And the first talk will be on Eta Carinae. It will be by Ryosuke Hirai. I hope I pronounce well. I'm sure I didn't. But yeah, well, the floor is yours. So if you can share your screen, and you have now 12 minutes to discuss. Go ahead.
Okay. Do you hear me?
Yes.
Yes.
Thank you. Yeah. So yeah. Thank you for the introduction. I'm Ryo Hirai from Monash University, and I will talk about Eta Carinae, and thank you for setting up the scene so nicely. So Eta Carinae is this star that you see in this picture. We know it's a luminous blue variable with a very massive mass, so it's like 100 to 250 solar masses. It's blowing a super strong bipolar wind with a record high mass loss rate. And we know it's surrounded by this so-called homunculus nebula, which is this bipolar axisymmetric thing. This thing was thought to have been created by this great eruption that occurred in the 1800s. And also the central star, we know it's an eccentric binary. But I also want to draw attention to not only the homunculus nebula, but there's also lots of structure in the surrounding nebula. So I'm not just going to talk about the homunculus, but things around it. So for example, you can see in this right bottom panel, where in the wider field, you can see these ejectiles. Yeah. So yeah, we have all of these ejectiles expanding outwards with different velocities. And if you track back their velocities back to the center, you can estimate their apparent ejection dates. And there have been multiple ejection episodes with century intervals, and each of them actually seem to be one-sided. So these blue arrows only occur in this side. There's only green arrows pointing in that side and that side, and then these yellow arrows pointing only this side. So, and all of these ejections seem to be random and unassociated to the symmetry axis. Now, other than these main details, there are all sorts of other details that are known from the observations, including we have some spectra from the great eruption light curves, and this very fast component which reaches up to like 20,000 kilometers per second, which is way faster than the homunculus expansion, which is like 600 kilometers per second. And also the optical caps of the homunculus is known to be slightly more optically thick compared to the side lobes. But in any case, any scenario has to explain all these things self-consistently, and many scenarios have been proposed in the past. But today I'm just going to talk about our scenario, but I know many people in this audience have their own favorite model. So our model is a stellar merger in a triple system, and I'll just briefly walk you through. So we start off with a hierarchical triple system with 3 stars with similar masses in a very stable configuration. But eventually the primary star would start transferring mass to its companion, and as the mass ratio flips, the orbit will widen and ruin the hierarchy of the orbits. And as it does so, the orbit becomes unstable, and it would cause some violent Kozai-Lilov oscillations where the eccentricity becomes so high, the stars can graze each other's surface and send out these outer ejectiles. And then eventually the 2 other stars will merge as the orbit becomes completely unstable. And yeah, so the other 2 stars will merge. But because these 3 stars were chosen to be almost equal mass, they have slightly like half established cores in the middle. So it will cause a common envelope phase, and these cores will merge at the center, release some energy, and cause a great eruption. But this eruption isn't enough to unbind the whole star like a supernova, so it retains a huge amount of energy and mass and angular momentum in the star. And this excess energy would be emitted, we think, in the form of super-engine winds. And also because of the rapid rotation, the winds will be bipolar, and this bipolar wind will sweep up the inner parts of the great eruption ejecta, creating the homunculus nebula. So this is our scenario. We try to verify this through numerical calculations. First, I'm going to walk you through the first half using triple dynamics simulations. So this is an example of a 3-body simulation. I'm plotting the the time evolution of the distance between the stellar components. And you can see the inner two stars have a very stable distance between them, but at some point, some secular unstable effects kick in. The distance becomes so small that the two stars, it becomes comparable to the sum of the radii of the two stars. And this peak kind of modulates over century timescales. And eventually the triple system becomes completely chaotic. It swaps companions and does its very cool stuff. And in the end, two of the stars will lead to a merger like this. Now, the post-merger properties of this particular system is very similar to the observed Eta Carinae system, but this doesn't matter because this is a chaotic system. Any different, slightly different initial condition can lead to a different outcome, but this is just a proof of concept that our scenario may work. Now, upon each of these very close encounters before the merger, we did some calculations to see how the surface material on the star would react to these very high eccentric orbits. So the red particles are test particles placed on top of the star, and you can see it interact with a companion star on a very eccentric orbit with different eccentricities. And above some threshold eccentricity, here you can see that the surface particle can be ejected. And if you recall the direction of the ejections, they are confined to the orbital plane, but also in this 90-degree opening angle. So if we combine this calculation with the previous calculation, we can calculate how these squirted out material will be distributed around the homunculus. Here's what it looks like. At the end, I'm just placing a homunculus, pretending the merger created it perpendicular to the merger plane. Now, if we look at this from the direction we see at Eta Carinae today and color the ejectiles in the way the observers did, we see that the distributions cooperatively match. So this sort of verifies the first half of our scenario, and here is our second half. So for the second half, we think a common envelope phase led to an energy injection and then to a wind sweeping up the inner parts. Now, we tried to do this in a 2D way, so we pretended there was a merger. So before the merger, there was a common envelope phase which created this very oblate torus-like envelope, and in the middle, the merger happens, so inject some energy and angular momentum there, and see how the explosion goes. Now, the explosion itself is actually quite spherical, but as I said, this merger product, there's a huge amount of mass still bound to the star, and this will eventually, we think, will emit super-Eddington winds. So we injected a wind from the middle and see how it sweeps up the inner parts. We also incorporate some radiative cooling to see what kind of shape it makes. And you basically see this homunculus-like shape. After about 160 years, it matches the size and shape of the homunculus we see as it is today. Now, this sort of verifies our second half of our scenario. So all is good. Maybe our merger in a triple scenario can explain the origin of Eta Carinae. But so does many other models in the literature. So that, as I think Noam said yesterday, we need to use all sorts of different metrics to test a model other than just saying, oh, it matches the shape of the observations. So here are some just example simulations from various people who reproduce homunculus-like structures. But I'm going to just point out what we can use to distinguish between these models by asking two very simple questions. So why is the homunculus thin and why is it bipolar? And all models do explain this in one way or another, but in different ways. So first, to answer the first question, why are they thin? So to create a thin lobe, you basically have to slam in a fast outflow into a slow outflow and have some efficient cooling. Now, outflows can come in two different ways. One is a wind-like outflow where you have a sort of constant velocity distribution over distance or over time. And also the other one is an explosion where you have a linear velocity distribution. And you can think of different combinations of these to have a fast thing slamming into a slow thing. You can have two different winds and have a thing shell in the interface. You can have a wind followed by explosion. Again, you have this thin shell in the interface. Or like in our model, you can have an explosion followed by a wind. All of these models have this, this interface where there's a fast thing slamming into a slow thing, but the main difference is the only model that can explain the fast ejector in the outer parts is this explosion followed by a wind. And also, other models predict a decelerating shell, whereas our model predicts a accelerating shell for the homunculus. So the homunculus is known to have accelerated in the past. So this may be an indication that the homunculus was created, at least in some sort of model that
2 minutes
where
left.
there's explosion followed by a wind. Okay, thank you. Perfect. Now, yeah, so this, so from the fact that there's some fast stuff outside the homunculus, and the homunculus has accelerated in the past, any model, you don't need to believe in our model, but any model to explain homunculus probably has to be an explosion followed by a wind. The other question is, why is it bipolar? So in the framework where we always need to have a slow outflow followed by a fast outflow, you can find the origin of the bipolarity in either the slow thing or the fast thing. So one way is, like in many models that we've heard of in the past 2 days, you can have a very equatorial slow outflow being followed by a rather spherical fast outflow. Or you can have a rather spherical slow outflow followed by a bipolar fast outflow. Okay, and you can have both. But because the polar caps are known to be optically thick, I think we need at least the fast outflow to be bipolar, because in this case, the equatorial part would be more optically thick. So any model, we need to follow these two different features: explosion followed by some fast outflow, and the fast outflow has to be bipolar. I'll keep my summary there, and thank you for your attention.
Thank you. Okay, so do we have questions? I don't have any in the Slack. I see one by Vincent Ick, and Ursula. So Vincent, please.
Hi. I don't have any questions really, except that, given the fact that we've been working here in my institute on the Eta Car, I really think this is a very, very interesting scenario. I, compliment you on your results. I really wanted to know, evidently, you would still want to do some more hydro because you end up with too many questions, really. So it's an open-ended question. What are your plans for the future?
Thank you for the question. But yeah, as you said, there's many questions still to be answered. One of the things we immediately were trying to do was first explain. So we have assumed that this merger product was followed by, the merger product would drive a super Eddington wind, but that's not immediately clear, because if you just simply dump in energy into a star, for example in Mesa, all it does is it expands and falls back, and doesn't naturally drive the wind. So we're trying to work on wind models to see how to keep a star compact and not expand and just drive the wind instead. But also, on the hydro end, there's many ways, many things we still need to explain. For example, one thing is, so in our model, in our model, because we had a equatorial outflow followed by a bipolar outflow, we still have this huge amount of material outside the homunculus. But according to the observations, there's absolutely nothing out there, which is actually hard for me, because to create a thin thing, you always need to slam in a fast thing into a dense slow thing, but apparently there's nothing out there. So maybe the whole thing is wrong. So we need to think of a way to get rid of this outer ejector outside the homunculus. I'm not sure if hydro is.
Thank you very much. I appreciate this.
Thanks. Ursula, please.
Hi, Rio. Thank you. What is the stability history of the orbits at the beginning? Because your dynamical simulation seems to go over, what, about 1,000 years? So what is the prior evolution? And was it stable, stable, stable until this point?
Yes, thank you. So we think it started off with a very stable hierarchical triple. The only reason it got unstable is because one of the stars evolves and starts mass transfer, and if it flips the mass ratio, it would widen the orbit, so the hierarchy of the orbits is ruined. And that's when we start our three bodies calculations. So this is like the mass transfer widening the orbit, and then we start this calculation. So there's like a million years of history before this simulation itself.
Thanks. Now I see a question by Getanjali Sarkar, please. We can't hear you. You need to unmute you.
Thank you. Yeah, this is more of a comment. Usually when we talk about common envelope, we always say, there's a great eruption and the envelope gets erupted. But recently, we came across papers by Glantz and Peretz where they are talking about, the in spiral of the binaries, or even in the triple systems, they've carried out some simulations where it leads to not an eruption, but you have pulsations, and it can cause, pulsations similar to what you see in AGB stars. And these might simulate mass ejections. I mean, we know pulsations are important for mass ejections in AGB stars. So that is probably another way of looking at why the mass, how the mass is ejected. The most common is, sorry.
Yeah,
I was just saying that we usually think of, just the envelope being ejected in a great eruption, but that is another scenario to it. So,
yeah, thank you. So indeed, I just want to point out that so before the great eruption, there were some of these smaller eruptions before it, and that indeed could be due to some instability in the envelope, but also I think Noam's just going to, or Amit is going to tell me that these are jets. But yeah, indeed, we could use those pulsations to explain these pre-great eruptions if we want to. But I don't know. We think these things may have been due to interactions with this bloated envelope with the tertiary star. So the tertiary star plunges in and out of the bloated envelope and causes these. But yeah, indeed, it could be due to these envelope instabilities in the envelope. Thank you.
Okay, I know there are still questions. I propose that you keep them for the discussion or you ask in the Slack, but we'll have to pass to the next speaker.